Hello, my name is Alex Davis. I'm an associate professor at Carnegie Mellon University in the Department of Engineering and Public Policy. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology.
And my name is Niles Guo. I'm a PhD student at Carnegie Mellon University in the Department of Engineering and Public Policy.
Today we're going to talk to you about public policy recommendation by optimizing an unknown social welfare function. So as a motivating example, consider trying to pick out a movie to watch on Netflix with friends and family, for example, at the holiday season. And so Netflix observes the movies that you watch and tries to understand your individual viewing preferences. So for example, it might create a profile for Niles based on the movies that he's watched. And Niles might have some friends, and those friends, again, watch some movies. And Netflix, again, records the movies that are watched by Niles' friends. And so Netflix is able to make construct a model of the preferences of Niles and his friend. The question is then, what if Niles and his friend want to watch a movie together? What should Netflix recommend? So this is a problem of going from individual preferences to a group preference. So we want to apply this Netflix metaphor to the policy sphere. So in the policy sphere, there are many individuals, and they have different preferences for public policies. We look at public policies with respect to energy futures in the US, and so different individuals might prefer wind or solar or nuclear power, and they each have their own individual preferences for what they think the US should do, and then they have to come to some agreement as a society. So this has been studied in the discrete choice framework for many years, where individuals are asked to make choices between different alternatives to model individual preferences. And then public choice behavior is represented as something like either market behavior or a simple aggregation, such as a equally weighted sum of individual preferences. However, we know from the behavioral science literature that individuals care not only about their own outcomes, but also the outcomes of other people in the society. They care about fairness. They care about people who are the worst off. And so we want to consider more than just an equally weighted social welfare function, but a social welfare function that might be defined by the participants or by the society themselves. So we want to leverage this existing behavioral science research to try to understand what is the right social preference function or social welfare function to best represent the group's behavior to promote compromise. And so if we can incorporate information about group behavior into the decision process, then we might come to a better group decision and have a better chance of consensus. So the way we think about this is drawing on the social welfare analysis literature, where under certain conditions of cardinal utility functions and fully comparable preferences across decision makers, that if those hold along with the Pareto criterion and independence criterion, then there's actually a very constrained functional form for the social welfare function. Here, the social welfare function for a particular individual I that takes as arguments the utilities of the individual utilities of all the different decision makers has to be a weighted average, an equally weighted average of the individual utilities plus a homogeneous degree 1 function G of the differences between the individual utilities and the unweighted averages, or the equally weighted averages. And so our hypothesis is that if we can learn a social welfare functional form that falls within this class of these homogeneous degree 1 functions, we can potentially allow for people to define the social welfare function that best fits their group preferences and potentially improve compromise. So we see this as a two-step challenge, and this is where we propose a new paradigm. The first step is to capture and model individual preferences from the participants, and we can use standard methods. Here we use standard discrete choice methods, assuming linear utility functions, and then try to figure out what the social decision rule is by seeing how individuals interact in a group and make decisions after considering many different alternatives. And this requires new methods. So our approach for learning the group's welfare function, we take two different approaches. The first is a weighted sum approach. So we just say the social welfare function has to be a weighted linear combination of the individual utilities, and then the task is simply to learn those weights. The second approach is a mean variance approach. And here, this mean variance approach can approximate several popular social welfare functions like the min, the max, variance averse, or variance seeking. And so here, the social welfare function that's being approximated is the equally weighted average, U bar, plus k, which is an unknown parameter that's estimated from the group choice behavior, times sigma, where sigma is the standard deviation of the individual utilities. So our approach is to observe individuals making decisions in a group after they discuss the alternatives, and then try to learn these parameters, either the weights of the linear utility function or the parameter k from the mean variance function, to best make a recommendation for the group.
Great, thank you, Alex. So I'll be talking a little bit more in depth about the research design and how we approach this issue. So for us to validate our approach, we decided to apply these two different algorithmic approaches to the problem of selecting a decarbonization strategy based on the set of climate policies proposed during the 2020 Democratic presidential primary. So if you remember back several months ago, a number of different candidates proposed very different climate change policies that were present during the 2020 Democratic primary. So we selected 4 different policy characteristics, each of them related to either some sort of a climate change policy, whether it's carbon tax, nuclear power, fracking, or a clean energy portfolio standard, with 3, 6, 3, and 3 levels each for each of these characteristics. That has a total of 162 different policy alternatives. This means that this problem of trying to identify the policy that has the highest probability of consensus is actually a non-trivial task. And we are using the criteria of group consensus as our criteria for evaluating this approach, because consensus is the only criterion where all social welfare functions agree on how to rank alternatives. Our participant pool are Pittsburgh residents who have identified that they're planning to vote or were voting in the Pennsylvania Democratic Party presidential primary. We chose that as our group sample size or sample population because they're more likely to pay attention to the media coverage of different climate change policy proposed by different presidential candidates, and also B, they're more likely to have stronger preferences on climate change policies. So our research consists of 3 different stages. During the first stage, we try to capture individual utilities. So participants were asked to make 44 pairwise comparisons, choosing between 2 different policy alternatives. So they interacted with a Shiny web app to conduct this discrete choice task. And once that's completed, we generated an individual utility function for all the participants. We then take all the individual each individual generated utility functions, and we divided them into 4 different clusters. This is done so that we can maximize the heterogeneity between the individuals when we move on to the 3rd stage of the study. So during this 3rd stage, we created groups of 4 participants, each drawn from each of the clusters I mentioned earlier. And then each of these groups were randomly assigned to 1 of 2 treatment arms. Each treatment arm either provided them with a recommendation generated through the weighted sum approach, or they provided a recommendation generated through a mean variance approach. We had 30 groups for each of the treatment arms, so 4 participants for each group. That means that we had a total of 240 participants for our study. During the last stage, so the stage 3 of the study, there were 3 further phases during this stage. The first phase is that each member in the group, as a group together, made 15 policy comparisons where they had to choose, or they had to make a decision on the group basis on whether the group preferred the left alternative or the right alternative. And during this phase, they had 2 minutes to discuss amongst themselves on which one is best for the group. Based on the answers for those 15 comparisons and also their individual utility functions, the algorithm then attempts to make a recommendation to the group. So the second phase is that the group members have to discuss this final recommendation and decide on whether they are willing to accept this or not. And the basis of acceptance is that this represents what's best for the group based on the discussions they've had and also their own individual preferences. Finally, after the group decides on whether to accept or not that final recommendation, we then validate that decision by asking 10 further recommendations, 10 further comparisons for the group to choose between the recommendation or 10 other alternatives that they have to select. So our preliminary results show that groups, when they're provided with the recommendation from the mean variance algorithm, they do have a higher chance of reaching group consensus. So on this plot here, on the left-hand side, shows the proportion of groups that had consensus or that reached a consensus for the recommendation. And you can see that 68% of the groups with mean variance reach consensus, compared to only 48% of groups when provided with the weighted sum algorithm approach. In addition, groups with a mean variance approach generate higher validation scores. So when we look at the total validation score for each of the group, we see that the distribution for that score is much smaller for the mean variance approach compared to the weighted sum approach. Summarize all of these data together, we do see some evidence that the mean variance approach do generate better results for the groups than the weighted sum approach. In addition, we could take all of these results and look at an individual level by observing how individuals voted while still controlling for the group effect. So here we employed a mixed login model and with a random, with a group level intercept to see whether each individual accepted the recommendation that was generated by the algorithm. And we can see that at the individual level, we still see that the individuals, when they're provided with a recommendation from the mean variance algorithm, do have a higher chance of accepting that compared to individuals who are given a recommendation from the weighted sum approach. This behavior is carries forward to when we examine the validation score. So we see that individuals, when they were provided with a recommendation from the mean variance approach, their likelihood of accepting that final recommendation is much higher than when the recommendation was provided through the weighted sum approach. And we see that on the individual level, there is some statistical evidence that the mean variance approach do generate both more likelihood of people accepting that recommendation and also a higher chance that people are willing to accept that recommendation against other alternatives when presented. So in conclusion, our study demonstrated a method to both elicit both individual and also group preferences and demonstrated a method to provide recommendations to a group. The preliminary results that we have so far show that the mean variance algorithm generated a better result, though we do need to conduct additional analysis. Some additional analysis that we want to conduct include examining how individual utility functions from their individual surveys change throughout the group negotiation task. We also want to examine whether individual utility functions drifted towards a particular cluster that we clustered individuals in during the second stage of the study. And finally, we also want to examine ex post which social welfare functions fit the best using cross-weighted RLC curves. So that concludes our presentation. We really do appreciate any feedback you may have with our plan analysis. And we have our contact information here on this slide. And we do want to thank one of our research grant sponsors, which is the Center for Behavioral and Decision Research at Carnegie Mellon University. Thank you.